continuing on with genetics, we're going to look now at how some genes are related to sex and how others are not. Now, the non-sex chromosomes are also known as the autosomes, and these do not show up in any differences between males and females. The autosomes are all the genes and chromosomes that have nothing to do with whether or not you become male or female. And so if we're looking at humans, where we have 23 pairs, the first 22 pairs are the autosomes. The last pair is the sex chromosome pair. And in this case, we're looking at XX, which gives you female, and XY, which gives you male. If a sex-linked trait is dominant, it's more likely to appear in females. However, if the sex-linked trait is recessive, it's more likely to be in males. The reason being is that typically females are XX and males are XY, and so when you look at these traits, they typically appear on an X chromosome. When you look at the recessive conditions, a female has two X's. So if she has one recessive allele, she has a second X to mask the first. But in males, since they are XY, they only have one X. And so if they have the recessive X allele, then they don't have a second X to mask the first one. The Y is actually a different size, shape chromosome that does not have the same genes on it. So we're looking at the X's and Y's. X chromosomes and Y chromosomes are different sizes, and they have different types of genes on them. One of the important ones is the SRY gene on the Y chromosome, known as the sex-determining region gene on the Y. This gene is going to basically kick on male traits and male genes. Now, I do want to make note that there are individuals who are intersex and individuals whose chromosomes don't necessarily match with how they present on the outside. Some individuals who are XX appear to be male on the outside, and some individuals who are XY appear to be female on the outside. And there's a variety of reasons of why that is, including things like androgen insensitivity syndromes and genes that have somehow moved from one chromosome to another. So I do want to point that out, that it is possible in some rare instances to be XX and male or XY and female. But for the sake of this class, we're going to simplify it down as saying XX is always female and XY is always male. Just keep it in the back of your head that sometimes things do go a little bit different. So we're looking at the X and Y chromosomes, and we see they're totally different shapes and sizes. And the allele we see here on the X is nowhere to be found on this Y. So if you're male, a single recessive allele on the X is all it takes to see that characteristic. There's no second X to mask the first. And there's a lot of different conditions that are related to X and Y chromosomes. Male pattern baldness is one, which is why sometimes you hear that it passes down from the mother's side, because it's passing on the X chromosome, and red-green color blindness is also found on that X chromosome. These are two very commonly known sex-linked traits. So both are carried on the X, which means both of these are going to be common in males. Now, if a male has color blindness or male pattern baldness, then we know for a fact he had to have inherited it from his mother. And that's because the X has to come from mom. The Y chromosome that they have has to come from their father. So let's go ahead and look at color blindness. There is a gene that basically produces light-sensitive proteins within the eye, found on the X chromosome. And there are two different alleles possible. The capital R, the dominant allele that produces functioning proteins, and the recessive little r that produces defective ones. So normal vision is considered dominant and color blindness is considered recessive. In order to be colorblind, the male has to have one colorblind allele, the recessive little r, from mom. But in order for a female to be colorblind, she has to have two little r's, meaning she had to get colorblindness from both her mom and her dad. To have normal vision as a son, as a male, he has to inherit his dominant R from mom. It doesn't matter whether or not his father is colorblind or not. And as for females, it doesn't matter who she gets the dominant allele from, either mom or dad. So this is why we see colorblindness in more males than females. Because females have that second X, they have that extra protection in place. It takes two alleles, meaning she has to have a recessive allele from both mom and dad. That means mom has to at least be a carrier for colorblindness, and dad must be colorblind himself in order for a daughter to be colorblind as well. It also means that if this female were to have any sons for herself, all of her sons, 100% of the time, will also be colorblind. Because the female here is colorblind, she only has recessive X's to give. Any son she has will also get that recessive X, meaning they will be colorblind.